A spacecraft is usually judged by how long it survives. In this field, survival is failure. The machine is built, guided, and instrumented so that its final useful act is to strike another world at enormous speed. A deliberate spacecraft impact is more than disposal. The impactor must arrive at a known place and time, while instruments watch closely enough to turn a moment of destruction into a controlled experiment. That control is difficult because hypervelocity changes the rules. At several kilometers per second, metal, rock, and ice do not meet like solid objects in an ordinary collision. They shock, fracture, vaporize, and throw material outward. The best mission, therefore, needs more than a dramatic flash. It must pose a precise question, get a measurable result, deliver the impact reliably, and leave behind knowledge or capability that could not have been obtained as well by gentler means. We will judge these crashes on 4 things: experimental design, quality of measurement, consequence, and transferability. A clever one-off result matters. A method that other missions can reuse matters more. There is also a brutal constraint. An impact experiment gets 1 trial. There is no second pass, no repaired instrument, and no chance to reposition the projectile after the final seconds begin. Across 5 decades, engineers have used that single chance as a seismic hammer, a shovel, a sampling tool, and eventually something far more consequential. Each mission made the crash less like an ending and more like an instrument. The contenders begin with an elegant act of recycling on the moon. They end with a collision whose success had to be read not merely in debris, but in the altered motion of a natural body. Apollo first showed how useful a spent spacecraft could become. After Apollo 12 placed a seismometer on the moon, later Saturn V stages were deliberately aimed at the lunar surface instead of being discarded into solar orbit. Because controllers knew when and roughly where each stage would strike, the impacts became calibrated seismic sources. The seismometer could compare a known artificial blow with natural moonquakes and meteorite strikes. The moon responded strangely. Signals reverberated far longer than a comparable disturbance on Earth, helping scientists infer a dry, fractured interior that did not damp vibration in the same way as wet terrestrial rock. This was resourceful and scientifically productive, but the crash remained an accessory to a much larger mission. The stages were powerful hammers, not purpose-built impact experiments, and their main achievement was revealing the target rather than perfecting the active impact. Lunar Prospector made the collision itself the final hypothesis test. Its neutron measurements had strengthened the case for hydrogen near the lunar poles, where permanently shadowed craters can remain cold enough to preserve ice. In July 1999, controllers sent the small orbiter into Shoemaker Crater. Telescopes on Earth watched for water vapor in the debris cloud, hoping the impact would turn a remote chemical hint into direct evidence. No characteristic water vapor signature appeared. That negative result did not erase the hydrogen data, but it exposed the weakness of the experiment. The expected plume was difficult to observe, and a non-detection could not cleanly distinguish absence from inadequate sensitivity. Deep Impact attacked a more ambitious target. The mission carried a flyby spacecraft and a separate copper-rich impactor, then released the projectile into the path of Comet, Tempel 1. While the surviving craft prepared to watch from a safer trajectory. The impactor navigated autonomously during the closing hours and met the comet at roughly 10 kilometers per second. Telescopes on Earth and in space joined the flyby craft in watching the flash and the expanding cloud. The collision excavated material hidden below the weathered surface. Observations revealed water ice, organic compounds, and a remarkably porous outer layer, with some analyses indicating that much of the near-surface volume was empty space. Deep Impact also demonstrated a useful separation of roles. One machine could be sacrificed, while another carried the cameras and spectrometer needed to interpret the event. That architecture turned destruction into a carefully observed excavation. Its limitation was equally clear. The mission was designed to expose a comet's interior, not to produce and verify a controlled change in the comet's path. The impact was scientifically rich, but the target's motion was not the experiment. Okros refined the idea with almost theatrical economy. It used a spent Centaur rocket stage as the projectile, and followed behind with a shepherding spacecraft packed with instruments. the Centaur struck Cabeus, a permanently shadowed crater near the lunar south pole. The following spacecraft crossed the rising plume, measured its composition, transmitted the data, and then struck the moon several minutes later. This time the plume answered clearly. The mission confirmed water ice and found other volatile materials in soil that may have remained beyond direct sunlight for billions of years, changing how scientists viewed lunar resources and chemistry. Okros is the strongest rival because its impact, observation plan, and scientific question formed one compact machine. Yet it still used a fixed lunar target to reveal composition. It did not have to find a moving body autonomously, or prove that a collision could deliberately change that body's motion. NASA's Double Asteroid Redirection Test, known as DART, is the GOAT of intentional spacecraft impacts used as controlled experiments on natural bodies. Its question was not what lies beneath the surface. It was whether a spacecraft could hit a small asteroid moon and measurably change its orbit, demonstrating a technique that might one day help prevent a hazardous asteroid from reaching Earth. The target system was chosen with unusual care. Dimorphos circles the larger asteroid Didymos, and neither body threatens Earth. From our viewpoint, their repeated eclipses cause small brightness changes that let astronomers time the moonlet's orbit before and after impact. That binary arrangement made the experiment measurable without waiting years to detect a tiny change around the sun. A shortened orbit around Didymos would provide a fast, clean signal that momentum had actually been transferred. DART itself was only about 570 kilograms. At impact, Dimorphos was roughly 11 million kilometers from Earth, and the spacecraft was closing at about 6.6 kilometers per second. Hitting the larger asteroid would have been the wrong result. During the final 4 hours, the camera called Draco fed images to an autonomous system called Smart Nav, which had to identify the smaller body and steer without real-time human control. The camera also served as the last witness aboard the impactor. Images streamed back to Earth as two distant points became separate worlds. Then, as the rough, boulder-covered surface of Dimorphos expanded to fill the frame. On September 26, 2022, the signal ended exactly as planned. The spacecraft struck Dimorphos, while telescopes across Earth and in space, together with a small companion probe, watched the resulting plume. A hit alone would not have won this field. The decisive measurement came from the orbit. Before impact, Dimorphos circled Didymos in 11 hours and 55 minutes. The first confirmed result shortened that period by 32 minutes. Mission planners had considered a change of 73 seconds sufficient for success. The measured shift was not a marginal detection. It was large, independently observable, and directly tied to the mission's stated test. The collision was also more effective than a simple transfer of the spacecraft's momentum. Material blasted from Dimorphos recoiled in the opposite direction, adding an extra push. Researchers estimated that ejecta substantially amplified the momentum delivered by DART. That detail matters because asteroids are not uniform billiard balls. Their density, strength, porosity, boulders, and loose surface material influence how much debris escapes and therefore how powerful a kinetic impactor becomes. Okros remains the neater chemical experiment. Its shepherding spacecraft flew directly through the material it had excavated and confirmed lunar ice. DART wins because it added a new level of consequence. The target's changed motion was both the measurement and the capability being tested. The limitation is serious. One successful strike on one small, loosely assembled asteroid cannot tell us exactly how every dangerous object would respond. A denser rock, a different shape, or an impact at another angle could transfer momentum very differently. That is why the experiment is still being completed. The European Space Agency's Hera spacecraft is on course to reach the Didymos system in late 2026, where it will measure the aftermath closely and help turn one result into a more reliable defense method. DART earns the title because it united targeting, autonomy, observation, measurable physics, and a practical consequence in one irreversible act. It showed that the greatest deliberate spacecraft crash is not merely one that reveals a world, but one planned early enough to help keep a world from being struck.